Okay, so let me introduce today's speaker, Anthony Clement. He was also one of Baumslag's students, and we had many classes together. Yeah, we used to study a little bit together as a group. Today he's going to speak about the Baumslag Solitar groups, the solution for the isomorphism problem. Thank you.
Thanks, Delaram, and thanks, Andrew, for inviting me to speak here. So, again, the title is the Baumslag Solitar groups, a solution to the isomorphism problem. So before we begin, we might just want to take a look at those maxed in 3 fundamental problems. And so in 1911, Max then gave 3 kind of fundamental problems that really drive the research in combinatorial group theory. And the first is, so given a finite presentation, FP, the word problem is, you could ask, is there an algorithm to decide whether or not any given word represents the identity in G? So given a word, can you tell whether or not that's the identity? So if you can, then you're able to solve the word problem in that particular group. The contingency problem is there an algorithm which decides whether or not any pairs of words, U and V, represent conjugates element in G? And if you're able to do that, you have solved the contingency problem. And the isomorphism problem that related to this topic is, given to a finite presentation, can you tell whether or not these 2 groups are isomorphic? Okay? So, before I start, let me just give you some historical background and motivation. So, there was this common belief in the early 60s and the 50s that every finally generated one-related group was Hoffian. Okay? That is not isomorphic to one of its proper quotients. And so, independently, Gilbert Baumslag and Baumslag Solitar came up with independent solutions of this to disprove this belief. And they came together and wrote a paper entitled Some Two-Generator, One-Related Non-Hoffian Groups. And it was published in 1962. So, and then they become famous. Okay? So the counterexample was an example like this. B23. And this is a presentation. It's generated by AB. And the relation is A inverse B squared A equal to B cubed. Now, the general form has this BMN, in which I'll be talking a lot. And the relation is just A inverse B to the MA equal to B to the N. M and N are integers, non-zero, any integer, whether or not it's positive, negative. So that's the general form. Now, before I continue, we might just want to take a slight look. Why is B23 non-Hoffian? Well, if we look at the general form, we can kind of classify the Baumslag Solitar groups in certain ways. Those which are residually finite. So BMN is said to be residually finite if and only if the absolute value of M is equal to the absolute value of N, or the absolute value of N is 1, or the absolute value of M is 1. Later on, I'll be able to throw away the absolute value according to what I want to do. And it's Hoffian if and only if it's residually finite, or M and N have the same prime divisors. So later on, we're going to see that from that 2 definition, we see that B23 is non-Hoffian. Because neither 2 or 3 have the same prime divisors, neither 2 or 3 is 1, and neither 2 or 3 is equal to each other. So that just shows, just from what I just said, it's non-Hoffian.
So that condition was proven?
Yes.
It wasn't a definition?
Yes, that condition was correct.
I proved it, you don't remember?
So just to continue, this is just like a sketch of the proof. So we have B23 and T1, these are so-called teacher transformations. So given a presentation, a finite presentation of a group, there are ways of taking that presentation, doing certain moves, and making other presentation isomorphic to that original presentation. These so-called moves are in the form of T1, T1 prime, T2, and T2 prime. They're called teacher transformations. And so suppose we consider this quotient. Now why is that a quotient? So we take in the group G, and we model it out by, first of all, the normal closure of this particular element. And what is the element? This here. The normal closure of that element in G. So we take in G modulo C, where big capital C is the normal closure of that particular element in G. So in other words, if we want to have a presentation, we just put up that relation in the, together with the original relation. And then we'll do some teacher transformation. We add C, a generator C, and hence we'll add a relation involving C with the other generators. And in this case, we'll just add C equal to B inverse, A inverse, BA.
So this is just B equals...
Yes, the commutator.
Exactly.
I agree, yes. B comma A squared. B equal to B comma A squared. Good. And
so you want to show that it's not up here?
Yes.
Okay.
So when we do a series of teacher transformation, we end up with this presentation here, which is isomorphic to G. However, it turns out that that element that we choose is also in the normal closure of B and G. And we can do a so-called Magnus breakdown of one related group. And it turns out that this normal closure of B and G, which involve teacher transformations, as well as not teacher transformation, but the Rademacher-Schreier method, that is representing, if you're given a presentation of a group and given a subgroup, we can actually present that subgroup. So it turns out that this normal closure in B and G has the form B sub B, there's an index, BI, and the relation would be BI to the square equal to BI minus 1 cube. So these are a whole series of generated infinite relations. And it turns out that that is an ascending union, by the Magnus breakdown, ascending union of generalized free products of isomorphic copies of a very special type of one-related group with cyclic amalgam. So there's a lot of work involved there. And later on I'll just talk about that. And because we'll have to just represent BI equal to A to the negative I, B times A to the I, we have this particular relation. And so it turns out that when we break up these groups, this particular word in terms of the BI, it will have in terms of subscript, B0 and B1. And because it's in this particular one-related group, we could further break it up into amalgamated products. The generator would be B0, B1, and the relation would be B1 squared equal to B0 cubed. So this is just an amalgam of two infinite cyclic groups with cyclic amalgam, if you understand that. Again, because of the normal form, this element is represented in an amalgamated product generated by B0 and B1. Because of the normal form of amalgamated product, this element is not one in the amalgamated product. So hence this element is not one in the normal closure of B and G, hence not one in G. So this shows that there's a proper quotient in which it's isomorphic to itself. Yeah, so a lot of the times people don't do it like this.
Yeah, I was going to say, usually you take a mapping.
Agreed.
Yes.
But because I like presentations and teacher transformations,
Don't disturb us.
I want to do it this particular way.
They should like presentations.
Not much people do it in this way.
So that last line there is not trivial at all.
No,
No.
you have to show that. A lot of work to get.
So we'll say clearly. And it's
But
Okay.
it is really the Magnus
Yeah,
Breakdown
yeah,
of one related group. Yeah.
repeatedly.
Right,
Yeah.
right. Okay,
Okay, so
there he is. Hey.
So we'll just have I'll give a concise proof of this theorem. Given G, BMN, presented this way, generators AB, relation A inverse B to the M, A equal to B to the N, and given a next group H, which I call BM prime N prime, equal to the generators are XY, and the relation is X inverse, Y to the M prime, X equal to Y to the N prime. Same procedure, N prime and not 0, and they are in Z. So then if G is isomorphic to H, if and only if G is isomorphic to H, if and only if M is equal to M prime, and N is equal to N prime. Now again, remember that is it for any particular integer. The notation, this is just the first derived group, G2, second derived group, G, a symmetry product of S by the infinite cyclic group in this case, because there's no element of finite order. But, and then we have G, this is the isomorphism to H via a particular, G is isomorphic to H via a particular isomorphism phi, and normal closure being G, the center of G, and the restriction of phi star.
What is S?
The normal closure of B.
The
It's
normal
not
closure of
under,
B.
so it's not written out, unfortunately.
Okay, good.
Which, here?
Yeah, the
That's
S
S.
is not written there,
Oh, that's S, I see.
but that's S.
Okay, good. Thank you.
Well, later on you will see, yes. We're gonna... Well, yes, okay, so S is...
But of course, everybody knows that, right?
Okay, except me.
Well, S and these are groups, S subgroups of
Well,
G.
you were talking about a very different element in the same group
Yeah, but I'm
before.
using the same letter,
Yeah.
so I'm just trying to be consistent here. This could be any
Consistently
subgroup of G.
suppressing information.
Okay, so the proof of theorem 1. So again, these are the reserved for this particular group, the BMN and the BM prime N prime. And the first thing that we must note, the reverse of theorem 1 is obvious. That is, if N is equal to M prime, and N is equal to N prime, then all we do is there's just a symbol by symbol replacement, A with X and B with Y, okay? So the real proof is the one, the forward direction. And so, again, since theta transformation shows that these two are isomorphic, again, we can show that, and that's where I will look at the n minus n, and so I can remove the absolute value whenever you choose the negative integers. So by this, we could always say n minus m is greater or equal to 0. Just choose any m and n, we can always make sure that when we subtract, it's greater or equal to 0. So I'll be taking a look at this particular form, n minus n is greater or equal to 0 for all m and n. Not 0, of course. So the proof of the next two lemmas can be easily deduced through some obvious observations and from Magnus' one-related group. Well, again, it involves some work. But let me just say a couple things. So this is a lemma. Let G equal to BMN with M